Our next speaker, Philippe from EDB, also one of our amazing sponsors. Wonderful to have them on board. He is going to be giving a talk about securing Postgres, doing things the right way there. So if we could bring him on so he can start giving his talk, that'd be great. Hello, sir. Welcome.
Thank you. Hi. Yeah, we'll be speaking again about Postgres. So get ready your drinking game.
Let's keep the party. We got it. The thing is, it's such a strong topic. I really mean that though. Like every time we've done live streams about Postgres, we really get a solid turnout. It really generates a lot of interest. And I have no doubt that your talk will do the same. So anyway, you can take it away. Go for it.
Okay. So as you said, I work for EDB and we'll be speaking about securing PostgreSQL on Kubernetes. So before starting, a few words about EnterpriseDB, or EDB as we were calling it. Our focus at EnterpriseDB is PostgreSQL. We are a PostgreSQL company with thousands of customers, employing a few of the founders of the project themselves, and we are one of the major contributors to the open source project. In the recent years, we saw an increasing interest in the cloud, as everyone is. So much that we just landed a preview for our own PostgreSQL as a service on Azure, which soon will reach GA, and then we'll move to a few other cloud providers. EDB and Kubernetes. For this reason, we at EDB has been investing a lot in Kubernetes lately. We were the first PostgreSQL company to become Kubernetes certified service provider. We are silver member of the CNCF, and we are also platinum founding sponsor of this awesome community, as you were saying. Moreover, we have 2 Kubernetes operators certified by Red Hat, and we'll be speaking about one of them. CMP, I think the slides got a little bit messed up, but no worries. So we were saying, I'm working in the team developing CMP, or Cloud Native PostgreSQL, which is an opinionated operator to run PostgreSQL on Kubernetes. So it's really on the same topic as Alvaro was speaking about. CMP is an opinionated operator to run PostgreSQL on Kubernetes. So as all operators, it is designed to take care of the whole life cycle of its operand, from the simpler things like self-healing, scale up, scale down, upgrades and major upgrades, to more complex things like backups, recovery, and replica clusters, and much more, as we'll see. So I said opinionated earlier. That's because going from the simple declarative definition you can see on the left to a running cluster means a lot of decisions we have to take. And most of them are security sensitive. That's why one of our focuses is to make CMP secure by default. What do we mean when we say secure by default? Kubernetes community came up with a model to think about cloud native security called the 4 Cs security model in Kubernetes. In this model, we have 4 layers, each of them building up on the next outermost layer. We'll give for granted the outermost, which is the cloud, as it's not something we can directly control. Instead, we'll focus on the 3 other layers: cluster, container, and code layer. So we'll start from the cluster layer. There are 2 areas of concern for securing Kubernetes: securing the configurable cluster components, so what Kubernetes gives us to configure and to set our application to be secure, and securing the application itself, which is running in the cluster. About the first, starting from the securing the configurable cluster components, one of the main things an application running on Kubernetes can do is explicitly setting its security context applying the principle of least privileges. So we dropped all the privileges we don't need by explicitly defining the security context in both the operator and the cluster pods, which for OpenShift means we can run with the default restricted security context constraint. We follow the same principle for RBAC, so for the role and service accounts and role binding part, but we will not go into the details as that alone would have requested a few slides. So about securing the application which run in the cluster, here are a few requirements about it we had and we posed ourselves. before starting developing and while developing CMP. All applications should possibly support encrypted communication both from inside and outside the cluster. We do not want to handle certificates manually because it's hard. And as we said, these should be the default settings, not some opt-in configurations. For both internal and external traffic, all instances are going to allow SSL connections with the provided SSL certificates. And here you can, in some way, because they all got messed up, see the configurations for both the server side on the upper side and the client string, the client connection string on the lower side. Client will then be able to verify they are reaching the right server by enforcing in the connection string the correct root certificate and root CA. About the client authentication, we support obviously basic authentication, but also support and encourage certificate authentication so that user can connect to Postgres instances just by providing a certificate signed by the right CA, which we will see we can handle. We support, by default, we support the operator will support to generate a self-signed CA, which then will be used to sign both the server and the client certificates. In this mode, the operator will also take care of rotating all the certificates when needed, but we also provide two other user-managed options to accommodate all possible requirements. An hybrid mode, in which the operator is given only an intermediate CA, which will then be used to generate the certificates necessary. And this can be applied to both the server and the client CA separately. And then a full mode in which the operator should only be provided the name of the required secrets containing the public part of the CA and the required certificates. And this allows to support tools such as Cert Manager or any other automation you could have in place, as long as it's using Kubernetes secrets, obviously. In default and hybrid mode, we also have an ND kubectl plugin that allows to generate client certificates for users using the in-cluster client CA. As you may know, PostgreSQL, and as Alvaro was saying, supports a leader-follower kind of clustering by default. This means followers have to connect to the leader instances as a user with some specific grants, always applying the principle of least privileges. So by default, they communicate securely by leveraging what we showed earlier, connecting via TLS using a client certificate for a dedicated streaming replica user, which is all handled by the operator itself in the automated or half automated modes. Another really important aspect is logging, and more specifically auditing when we talk about security. PostgreSQL supports logging to files in CSV or syslog format, and the same goes for the most used auditing extensions such as PG Audit or EDB Audit if you are using EPAS, EDB PostgreSQL Advanced Server. But given that we are running on Kubernetes, we don't want CSV logs. We want JSON formatted logs, and we want them on standard out. So we could have added one more sidecar to the Postgres instances, as Alvaro was suggesting, but running something like FluentD or FluentBit, reading and parsing all logs and outputting them to standard out. But as we learned, log formats can change between Postgres versions, and these projects are much more complex while we only care about Postgres CSV logs. So we implemented it ourselves, setting PostgreSQL to log on a few FIFO files in CSV, which a small Go routine is reading from, parsing them, and outputting them in JSON to standard out. This way, we are able to parse the logs correctly for all the supported PostgreSQL and EPAS versions for standard logs, PG Audit, and the DB Audit logs. Here you can see how setting some PG Audit specific settings, parameters in the cluster configuration will result in some nice JSON formatted logs on standard out, which you can see on the right. And also we will automatically enable the PG Audit extension in all the reachable databases. Going back to the authentication part for a second, in PostgreSQL, client authentication is controlled by a configuration file, which traditionally is named pghbaconf. We set a few default parameters that we need for the cluster to work properly. Rules are matched in order, so we have a few lines on the top, which are, let's say a header on the top, which allows all local connections to all databases and for all users to be authenticated with the peer authentication method, which means the Postgres username must match the OS user. Then all SSL connection for the user streaming replica to both the Postgres and the replication database from all IP addresses should go through cert authentication, and then you can inject your own rules as shown on the right. And in the default and then the default for all connection from everywhere for all users and all databases, they're going to be authenticated with MD5, like some kind of fallback, last fallback. So the first C is about containers, which means you have to build and run containers with care, and we'll see. The usual rule of thumb is one application per container. This could lead to have a lot of sidecar containers, one for monitoring, one for logging, one for service meshes, and so on. Sidecar containers are a useful pattern, obviously, to extend an application, but probably more to extend an application with some add-ons. But still, coordination is kind of hard, and like Istio does, you could end up with some magic tricks you can really not understand if you're not really into it. So that's why we decided not to adopt this pattern. Instead, we decided to inject a single binary through an init container, which is then going to wrap the actual PostgreSQL process, handling everything it needs to run Postgres properly. We build a lot of images, both for the operator and for the operands. So PostgreSQL and EPAS, Enterprise PostgreSQL Advanced Server. We host them on Quay.io and on Docker Hub. And we regularly, and more importantly, we regularly scan them for vulnerabilities and rebuild them as soon as fixes are available upstream for any package installed. So about Operand images, we have a few options there, mostly to reduce and to, let's say, be compliant with the Red Hat certification and all the other certification and all the requirement of our customers. So for the PostgreSQL images, we offer both a Debian and a UBI-based image, and then we support a few versions, all of them checked and rebuilt, all of these images checked and rebuilt once a fix in all the additional packages installed are released upstream. And we also install all the additional libraries required by CMP, such as Barman Cloud for the backup part, PG Audit, PostGIS, and the Docker files are available online. About the Enterprise PostgreSQL Advanced Server, we only offer UBI images. We have images for all the supported versions and all the needed additional libraries. But once you are sure an image is scanned for known vulnerability and that it's rebuilt, every time a fix is available, you want to be sure about what image you are running. So for this reason, we support specifying the image digest, and you should specify the image digest and not just the tag for the image. In this way, you are going to be precisely sure about what's running in your cluster, and if you pair it with some kind of flavor of container or image signing mechanism like Notary or Sigstore right now, if you are into it, you can be sure that the image you are running, it's exactly the one built and you recognize it as the one built by who you trust. The last and most internal C is about code, as application code is one of the primary attack surfaces over which you can have the most control. So we put in place a rigorous process Why? Because code is probably the hardest part of all of them. That's why we have an always evolving process to be sure to ship the best code we can to our users. It all starts from the developer on the left, who writes a patch. The patch is then pushed to Git in a development branch, and the developer issues a pull request according to the GitHub flow that we adopt. This triggers a GitHub action that executes automated tests, unit tests, and static code analysis through linters, which allow us to shift left as many issues as possible. If everything passes, we build our container images, which then are used to run a set of end-to-end tests against all the different versions of Kubernetes we support. Firstly, using Kubernetes in Docker. So we run a suite of tests against all the different versions of Kubernetes in a, let's say, restricted environment. We can spin up when we need it. But then we also run end-to-end tests against all the supported cloud providers and OpenShift supported versions. So we have a really big and huge suite of end-to-end tests that allows us to ship code we think and we believe is working as expected. We also run end-to-end tests when merging, so before merging, so after the patch has been pushed, a few reviewers, surely at least 2 reviewers review it, all the tests pass, we merge it in main, and then again, all the tests are run again to check if everything is fine, and then a release is done once we are ready to release the new version of the operator.